Hello and welcome back to the course on deep learning. So we've learned quite a lot in this section of the course. Let's summarize what we've talked about. All right, so here we go. We started with an input image to which we applied multiple different feature detectors, or also called filters, to create these feature maps. And this comprises our convolutional layer. Then on top of that convolutional layer, we applied the ReLU, or rectified linear unit, to remove any linearity or increase nonlinearity in our images. Then we applied a pooling layer to our convolutional layer. So from every single feature map, we created a pooled feature map. And basically, the pooling layer has lots of advantages. The main purpose of the pooling layer is to make sure that we have spatial invariance in our images. So basically, if something tilts or twists or is a bit different to the ideal scenario, then we can still pick up that feature. Plus, pooling significantly reduces the size of our images, and also pooling helps with avoiding any kind of overfitting of our data or of our model to the data, because it just simply gets rid of a lot of that data. But at the same time, pooling preserves the main features that we're after, just because the way it's structured, and the pooling we used was max pooling. Then we flattened all of the pooled images into one long vector or column of all of these values, and we input that into an artificial neural network, and that was step 3, flattening, and step 4 is the fully connected artificial neural network, where all of these features are processed through the network, and then we have this final layer, final fully connected layer, which performs the voting towards the classes that we're after. And then all of this is trained through a forward propagation and back propagation process, and lots of iterations and epochs. And in the end, we have a very well defined neural network. And another important thing is not only the weights are trained in the artificial neural network part, but also the feature detectors are trained and adjusted in that same gradient descent process. And that allows us to come up with the best feature maps. And in the end, we get a fully trained convolutional neural network, which can recognize images and classify them. So there we go. That's how convolutional neural networks work. And now you should be totally comfortable with this concept and ready to proceed to the practical applications. If you'd like to do some additional reading, then there's a great blog by Edith Deshpande from 2016. You can see the link over there at the bottom. So the blog is called The 9 Deep Learning Papers You Need to Know About Understanding CNNs Part 3. And this blog actually gives you a short overview of 9 different CNNs that have been created by people like Jan LeCun and others, which you can then go ahead and study further. So there will be a lot of new things that will be totally new to you and that you will have to get your head around. But just keep this blog in mind, or these 9 papers in mind. And even if you're not ready to go through them right now, maybe after the practical tutorials, maybe after you do some additional training in the space of deep learning, slowly you can then reference these works. And ideally, I think you will get a lot of value through looking through other people's neural networks and how they structured their convolutional nets. And that will help you understand what are the best practices and why people did certain things in a certain way. And that will help you with your architecture of neural networks, because neural networks and convolutional neural networks are not an exception. They are like an architecture challenge. You have to come up with a idea and then structure it and then adjust it and tweak it to get the best possible design and the best possible and optimal performance. So there we go. That's us for today. I hope you enjoyed today's tutorial and this whole section, and I look forward to seeing you next time. Until then, enjoy deep learning.